Welcome back, ladies and gentlemen. We're going to be looking at motion of objects to begin our study of physics improper. We're going to be looking at motion for quite a while. There's lots of ways to check this out, and there's different kinds of motion that we are concerned with. But how do we describe motion in an easy to understand way, in a simple way that's direct and that everybody can follow? We need to understand, we need to track sort of where things are and when they are at those locations. So where it is and when is it there. So where, that's like position. We don't know where it is, that describe the position of an object. And when, well, that's obviously time. We're concerned with positions and times when we're looking at motion. And if it's moving, the position is changing, and we're concerned with how quickly the position is changing. That's not so bad, right? So we've got little Nemo. He's on his way to try to track down something in the reef, and so he's going to start here. We mark a location where we're starting to watch Nemo's motion, right? And let's say 1 second later he's here. You can track that location. 1 second later he's here. Track that location. 1 second later he's here. And 1 second later he's here. And 1 second later he's here. So look at what's happening. We are marking locations with these dots. And so these dots have a distance between them. And what we're doing is as if you were following what I was saying, was 1 second later he's here, 1 second later he's here. We're looking at Nemo's location every second. So this is also important that you realize 1 second goes by between each dot. So for how long were we tracking Nemo's motion? Well, we have 1, 2, 3, 4, 5, 6 dots. However, no time had gone by when we made that first dot. After the second dot, 1 second had gone by. So there was 1 second, 2, 3, 4, 5 seconds. 5 seconds had gone by. How far did he go? Well, he went there, and then he went there, and then he went there. What we would have to do is measure these distances and add them all up. And so we get our handy dandy ruler. And we say, you know what? That's about 3.5 centimeters. That's close to another 3.5. Excuse me, close to another 3.5, and close to another 3.5, and close to another 3.5. What's 3.5 times 5? 15, 17.5. So our distance, so we have a time, and our distance, 17.5 centimeters. Okay, fair enough, no problem. We could also represent this as like information in a data table. We could say, all right, I'm going to look at the time here, measured in seconds, and I'm going to look at the location, and that's going to be measured in this case, in centimeters, right? What was the location when time was 0? Well, Nemo hadn't traveled anywhere yet, right? He was there. So there was 0 centimeters traveled. And after 1 second, 3.5 centimeters traveled. After 2 seconds, where was he? We're talking about location. He was at a location that is now 7 centimeters away from where he started. So we're starting to see something here. Location, another word for position. And so we would just kind of look at that, and then we keep going. After 5 seconds had gone by, he was at position 17.5 centimeters. Cool. Note the spacing between the dots. The distances between the dots is all the same. So what does that mean for us? Well, that's actually very important. Same distance in equal amounts of time. So what does that mean? So let's see, 3.5 centimeters in 1 second. And here's another 3.5 centimeters in 1 second. You know what I'm doing here is I'm doing a distance divided by a time. 3.5 centimeters in 1 second, right? And it's the same. It's the same. So distance divided by time. Well, centimeters per second is how you can say that. And so we can say, look, as long as the distances are the same in equal amount of time, we can say constant speed. I'm going to put speed in quotes because there's something else important as well, and I kind of hid the arrows, and I'm sorry about that. Let me do the arrows one more time here for you. I'll just kind of do them in between the dots right here. Arrow, arrow, and so on. All right. Not only are those arrows the same length, so we have the same distance traveled in equal amounts of time, the arrows are all going the same direction. And so we can say more about this. Not just constant speed. There's a new word you're going to learn, and it's called velocity. So we are also going to say constant velocity. Think of velocity as equal to, I'm not writing an equation here, just kind of a definition. Constant velocity. Velocity is more or less equal to speed and direction. They both matter. Okay, so we're going to use this word velocity as much as we can because it also indicates the direction of something. If Nemo had turned around and started going this way, Nemo still could have been traveling at 3.5 centimeters each second. But because the direction would be different, he would have a different direction here. That means he would have a different velocity. Maybe to the right is the positive direction. We're going to have some indication of which way is positive. That's going to matter to us. All right. But then when he turns around, he's now going in the negative direction. So at first he has a positive velocity. Then going back, he would have a negative velocity headed in the negative direction. Okay, now, what else can we do though? So check this out. Something kind of crazy for you. What if Nemo is just hanging out, just chilling, right? This is page 2. And he's startled by the barracuda that he suddenly notices in the water, and he's going to swim away. So he starts here, and at first, he's not going very fast. So in the first second, he only gets this far. But he's continuously trying to speed up because he really, really wants to get away. So in the next second, he makes it that far. And in the third second, he makes it that far. And in the fourth second, he's way over here, that far away, right? So what did Nemo accomplish? Let's check this out. We have an arrow there, then an arrow here. So we have distances that we're marking. And the distances obviously are getting larger and larger and larger with each second. So right away, you should be noticing that you have a distance. We can use this as distance if you like. The delta, the triangle is called the delta. Now what it means is when you see that right there, let me make a note here. You would say change in something. When you see the triangle, that's what it means. So we're talking about change in position. I know this is going to be confusing. D is really about position. So where is it? We're still talking about that. So the change in position is small at first. If we want to talk about the velocity that's taking place here, at first we have a small change in position in a certain amount of time. Lowercase t will be time. Next we have a larger change in position in the same amount of time. Here we have a very large change in position in the same amount of time. Well, what does this business right here mean? We change the position divided by time. Well, that is velocity. So what's happening to our velocities? They're getting larger. So we could say, well, we got a small velocity there, then a larger velocity there, then a much larger velocity there. Those are V's, by the way. V for velocity. Nemo is speeding up. And what we say is the object, Nemo is the object, is accelerating, right? Speeding up, accelerating. We can look at this differently. Okay, Nemo is safe. He's clear of that barracuda. This is different now. And so he's going to start slowing down because he wants to rest for a little bit. So at first, he's still going fast. He's right here. He's got a large velocity. Then 1 second later, he's there. He's starting to slow down. He's covering less distance every second until finally he comes to rest. He has stopped. So you can see that the slowing down, there. The arrows are getting shorter and shorter. So here's a large velocity. Here's a somewhat smaller velocity. Somewhat smaller velocity. A little tiny velocity, and then he stops. All right. We don't want to have to make these dot diagrams though every time, right? They're slow. They take up a lot of space. There's something better that we can use. So stay with me on this. This will be the last little bit of this video. All right. If we are going to track how the position changes with time, we usually measure time in seconds. Position can be anything. I'll stick with centimeters for now. It kind of doesn't matter. Okay, if we're going to track this, and we have numbers here. So at 0 seconds, let's say we're going to start at a position of 0. We're going to start at what we're going to call the origin. And that can be anywhere, just where we'd start looking at the object. 1 second later, it is 10 centimeters away. 2 seconds later, it is 20 centimeters away. 3 seconds later, it is 30 centimeters away. Okay, so what's happening here? Well, we can graph the data, right? We're going to make what's called a position time graph, a PT graph. And real quickly, what we're going to simply do is, if you recall graphs, we need an independent variable and a dependent variable. Well, look at this. Which one of these are we calling the independent variable? Which one of these are we watching to see what happens? And which one of these do we simply say, you know what, it's not that we're in control of it, but it's just the one that's happening. We're looking at position. We're watching the position change. That's the one that depends on the time, how much time has gone by. So here's our independent variable, time. Here's our dependent variable. Put the independent variable on the x-axis. So axis arrows. I'm going to have time measured in seconds. I'm going to have position. Now this is kind of silly. Position is our change in position, like that, delta D. My units are centimeters. Okay, so now at 0, 0, right? This is just like in math class. 0, 0. Then I have at 1 second, 10 centimeters. So let's just say 1 second is there, and let's say 10 centimeters is there. I really don't have graph paper. You can see why graph paper makes things easy. At 2 seconds, I've got 20. So at 2 seconds, there I got position. At 3 seconds, I've got 30. So at 3 seconds, I've got 30. Roughing this in by hand, of course, makes it not all that pretty. You can see the dots don't line up really well. But, okay. Cool. This is a position time graph of whatever this object is. I'm not really talking about Nemo anymore. Not necessarily. It could be any object. And it started at a position of 0. 3 seconds later, it was at a position of 30 centimeters, if we're counting by tens. Now, the neat thing here is I've got a line on a graph. Anytime you have a line on a graph, you should automatically think about slope. Oh, oh man, why does my math teacher want me to learn this stuff? I'm never going to use this stuff. Guess what? Here you are using it. Slope of a line. Slope of a line is simply a change in the y values divided by a change in the x values. What are the y values? The y values are position. All right, so I have that divided by change in time. I usually don't write the delta t, the delta in front of the t, just so you know. We will almost always be using 0 as our initial time with whatever we do. Just for simplicity, I don't know. Maybe I'm lazy. But what is this business equal to? Right here. Well, that change in position over time, that is your velocity. All right. Why not call it speed? I mean, it's just how far it went in how much time. Why not call it speed? Well, is it possible to have a negative slope on a graph? Well, sure it is. And that would indicate you'd have a negative velocity, but the speed would still be a positive value. If you imagine a speedometer in a car, the speedometer never gives you a negative value. It never gives you a negative speed, even if you're going backward, right? It's always a positive speed that you have. Velocities can be negative. So that's why we don't say speed. We're going to use the term velocity. So how would you figure this out? Well, you would really want to say, I'm gonna take like this spot on this line, I'm gonna take this spot on this line, and between those, I'm gonna say, you know what? I have a change in the x values of those two dots, and I have a change in the y values of those two dots, and that's gonna get me the slope. Notice I didn't pick dots that were my data points, and I selected two spots on my line of best fit that are kind of far apart from each other. Those skills are pretty important. You want to do it that way. All right, so what have we seen so far? We have seen how you can start to track the motion and sort of quantify the motion. Describing it, you can use a dot diagram. Where is it every second? And then how far has it gone in each second? You can use a data table. You can calculate a speed or a velocity. Remember, this is pretty darn important. I'm going to emphasize this a lot, that the direction that is positive really matters. It's easy, and sometimes you get to pick which way is positive, but once you do, you have to remember that. You have to use it. Okay, so what else? We've seen that, well, you know what? Velocity can change. It can be speeding up. It can be slowing down. And we've also seen that we can, instead of those sort of cumbersome dot diagrams, we can make what's called position time graphs. We're going to use these pretty regularly. We're going to look at these in more detail in class and in some lab activity that we're going to do. And it's nothing magic. We're just going to be using terms, practicing symbols, remembering that a delta D loosely means the position or the change in position of something, and then t is time, not a problem. And then the slope of a PT graph. Remember this. This is, I guarantee you, this is a test question. Slope of a PT graph equals velocity. Memorize that. It's a test question every single time. So there we go. That's the beginning of how we're going to start looking at motion. Thanks for watching. I'll catch you next time.